Hello, everyone. Let me welcome you to this evening's talk. It's a great pleasure that we have so many people here tonight to listen to this exciting talk. If you don't know me, my name's Athene Donald and I'm the Master of Churchill College. And it's great to see so many people here, as it were, in this virtual world. I hope this talk today will be both illuminating and exciting. It's certainly an important topic. So I'm delighted to introduce Professor Jenny Nelson as the speaker today. Jenny is an alumna and honorary fellow of Churchill, and she's, perhaps more importantly, Professor of Physics at Imperial College London, where she's researched novel varieties of material for use in solar cells since 1989. Her current research is focused on understanding the properties of molecular semiconductor materials and their application to organic solar cells. This work combines fundamental electrical, spectroscopic, and structural studies of molecular electronic materials with numerical modeling and device studies, with the aim of optimizing the performance of solar cells based on molecular and hybrid materials. So that's the physics side with which I'm most familiar, given if it isn't so far from my own research field. However, more relevant to tonight's talk, which I think and perhaps hope for all your sakes will not be overly technical, and that may reassure those of you whose physics is a somewhat distant memory. Since 2010, she's been working together with the Grantham Institute for Climate Change to explore the mitigation potential of photovoltaic and other renewable technologies. I look forward to hearing about her work in this arena, an area which is so important to us across the world. And can I just say that if you have questions, do insert them in the Q&A at any point during the talk, and we'll get to questions at the end. So now it's my great pleasure to introduce Professor Jenny Nelson. Over to you.
So thank you very much, Athene, for the introduction. It's a pleasure to be here. It would be a greater pleasure to really be there. It's more than 40 years since I started my undergrad degree. This time 40 years ago, I was actually in my first year of natural sciences as an undergrad at Churchill College. Indeed, I couldn't have imagined anything that would have happened between then and now. But anyway, that's part of the reason why I'm here today, connection with Churchill. And I shall be telling you about our research on this, if you like, part two of my sort of research agenda. So before getting into it, I would like to particularly thank my co-workers who've been involved in the work I'm going to talk to you about today. Phil Sandwell has been a very important person. He's a postdoc now. He was previously a PhD student in my group. Hamish and Paloma are PhD students. Habby was a master's student who actually did some fantastic work that I'll mention later on. He's already gone. Oyton is a research fellow who's still with us. AJ is my colleague in the Grantham Institute is a colleague in AJ and Sheridan, both colleagues in the Grantham Institute for Climate Change, and Chiara is another colleague who's an expert in energy economics. And they've all been involved in different ways with this research program I'm going to tell you about. So I'm going to start here, which is kind of this sort of interface between basic research and research which is really very applied. So I'm one of a number of people at Imperial who are working on materials for solar energy conversion. And that's a fairly, I work on materials for solar cells and primarily, but there's a larger community, of course, of scientists, chemists, physicists, engineers, working on materials and devices for energy conversion. And that work is very much, particularly nowadays, motivated by the drive to find lower carbon sources of energy. And that does mean at some point you need to ask the question, if these things that you're working on, if you could actually achieve the goals in terms of efficiency or performance that you're targeting, it would be very nice to know what difference would they make. And that question about 10 years ago led me into discussions with colleagues in the then newly established Grantham Institute for Climate Change at Imperial. And at the Grantham Institute, this was a sort of philanthropically funded, in the first instance, institute with the goal of addressing the interface really between low carbon technology development and policy. And one of the things that the colleagues in the Grantham Institute were doing was developing sort of scenarios or pathways that would sort of indicate how different technologies would be used in a pathway that might be targeting, let's say, a maximum 2 degrees or nowadays 1.5 degrees increase in global energy temperature. And so it was quite interesting to then think, okay, is there some way that we could sort of try to interface our work with these sort of tools that could help to ask questions in a global sense? So coming back to sort of where I came from, so for the last probably 20 years, my main research has been focused on soft electronic materials. We used to call them plastic, but basically carbon-based electronic materials and their applications, and particularly to solar energy conversion, so also known as organic solar cells, organic photovoltaics. And that's a research area that involves sort of understanding materials, looking in detail at the process of a photon absorption, a charge transfer event, and then the generation of electrical current, and how that depends on the chemical structure and design of materials that you make. And more recently, I'm partly actually motivated by what I've learned from the policy-related research. I've extended that to look at using similar materials in photocatalysis and also for charge storage. So that's kind of a sort of an area of materials science, applied materials science research. But with all of these topics, I mean, the goal in the end is to develop materials and devices that will be able to be used to assist with renewable energy generation, and would themselves have an advantage of having a relatively low emissions impact. And one argument for using these kind of easily processable electronic materials is that compared to sort of more traditional materials that have to be processed at high temperature or high pressure, they cost relatively little energy to make, and they are also relatively easy to recycle, and so they could play a part in a circular economy. So there is that argument. So there's arguments to kind of investigate these materials, but it was still relevant to ask the question, how much could they actually help? And that was the question that I kind of went to when I made friends, so to speak, with the Grantham Institute around 10 years ago. And it then led me onto a journey of doing different types of analysis that I'm going to tell you about today. So the first question is, if it all works out, what difference would it make? And so the very first thing that we did was we decided to do to implement an analysis in terms of the energy requirements, materials requirements, and the costs of the production process that we envisaged using for our plastic electronic materials when manufacturing them as solar cells. And then from that, so that would allow us to look at the impact of production and materials on the costs and the emissions together. And that work then led us to think about the use of our PV technology in a larger context. So in fact, you know, it would be used together with other elements in a system. It might be a grid connected system, or it might be indeed an off-grid system to provide electricity access. And then you need to consider more things. You know, it's a more complicated problem. We need to consider the role of the storage, the competing role of fossil fuels that might be available, and so on. And then, having developed tools to do that, we then started to look at how those tools could actually be used in practice. And that led to some other projects, which I'll mention briefly today. And then most recently of all, we sort of returned in a way to this kind of materials accounting question to try to apply a measure of energy accounting. I'll explain what that is later on, as a way to try to evaluate different low carbon or mitigation options in general. So this graph basically sums up the things that I'm going to talk about today. And I'm going to start with the focus on just a few comments on this work that we did early on, looking at the life cycle and cost analysis of materials. This is just another way of kind of looking at the same sort of space, if you like, that we care about when we want to think about the question of what would be the impact in the end of developing a new technology or a new way of making a technology. That involves thinking about the sort of the manufacture. What do you need to spend in terms of materials and energy inputs, and also money? How will it perform when you integrate it into a system with other technologies? And then in the end, how would you deploy it? What are the other issues? What in the end would be the impact on greenhouse gas emissions compared to not having developed the new technologies? That's kind of the big picture. So to go back to where we started, as I mentioned, I was looking at solution processable plastic, molecular semiconductor materials that could be used in solar cells. And these materials were very attractive initially from the standpoint that the devices could be made cheaply compared to the then sort of processes that were used for silicon or other inorganic solar cells. And the process would be something that's based pretty much on a kind of high throughput printing or coating process, where you'd start off with an electrode and then you put down layers on top of that, layers to collect the current on either side, and then your active layer in the middle, which is the one that would absorb the light and generate the electric current, electrons and holes from the light absorption. So we, in order to make an analysis of the energy input and the cost of this process, we worked together with colleagues in the Danish Technical University who were developing a prototype printing sort of procedure to make such solar cells, and they shared with us information about the quantities and the processes and so on. And I had a very talented student. Actually, Chris came first of all as a visitor, wanting to get some research experience after he finished his degree, and he ended up staying to do a PhD. And this was the first project he did, was the accounting for this exercise. And then the point I want to make here, so we took a process. This is actually a photo of the setup in the Danish Technical University. This is just a cartoon of our the way we do the elements in our counting. And then we come out of this with a kind of, you know, if you like, a bill of materials that's telling us how much energy is spent on the different components. And one of the things that this told us was straight away, there's one big component. There's like a showstopper, if you like, in terms of the energy required. And that is that one of the components, this indium tin oxide conductive layer that was put on top of the plastic substrate, was going to be the most important component and actually influence the effectiveness in energetic terms and in cost terms of the device more than any other component. The same thing comes from the energy and the cost analysis. And so what that told us at the time was, if you're thinking about what's the most effective thing to research, if you want this type of solar cell to sort of be as effective as possible, it actually makes more sense to go and try to find another material to use as a conductive electrode than indium tin oxide, than it does to improve the active layer efficiency by a factor of 2. I mean, so it was that big of a difference. It makes much more difference. On the whole, when you think about sort of the energy and cost balance, it would be much more effective to find a better electrode material. So that's just an example of how doing this type of analysis could actually help us to sort of try to direct the research into a better direction, if you like, given the end goal. It's just one example. So we then sort of, we did our life cycle analysis of our organic solar cells. We looked at how they are now, how they'd be in the future if if economies of scale begin to kick in. And then we decided what we really need to do is to look at how different PV technologies would compare in practice, in a practical situation. And we decided to make that comparison by considering an off-grid PV system, a PV minigrid. And part of the reason for that is because one of the biggest opportunities for solar photovoltaics is in electrifying the developing world, or providing, I should say, electricity access to the developing world, because there's a huge need. There's a very large number of people still without access to electricity, or even if they have access to electricity, quite often it's intermittent. And it's precisely, these are precisely the countries that are still using a relatively small amount of energy. And so in the development, in the course of development, they have the opportunity to kind of go straight to low carbon technologies without passing through the phase of fossil fuel dependency, which Western countries like ours are dependent on. And of course, governments and agencies and communities working in all these countries are very, very interested and active in taking up renewable energy. So it sort of made sense for us to think about the role of PV in a kind of an off-grid setting, because it's a complete no-brainer in terms of whether you should do it or not, or so it seemed to us. And also it also provided us with a relatively closed system in which we could make quite easy comparisons without needing to think about the entire electricity network and all the other power sources. So that was our kind of motivation. And just to kind of maybe comment on the potential impact of this. This is a sort of headline that came out of a study published last year by an institute in Berlin, the Rainer Lemoine Institute. And we would agree with their findings here that up to a gigaton of CO2 could be saved by off-grid electrification. And this is when you make a comparison between low carbon development pathways and the sort of the default, probably diesel and kerosene based pathway developing into fossil fuel electricity. So there's definitely a significant saving that can be made. And of course, later in the century, that saving is going to be much, much bigger as development proceeds. So it makes sense to look at this question. So the work that we started with, we made a fairly primitive model. We included in our model a PV generator, batteries. We considered different types of PV, different types of batteries. We then included diesel generator, as a diesel is the sort of standard option for electricity in off-grid locations, and then modeled the sort of supply and demand for a sort of communities based on knowledge that we had of electricity demand in different areas of India. And we considered some different locations which would differ in terms of the climate and therefore the solar resource, and also in terms of the terrain that would influence how easy or difficult it was to get a grid extended to those areas. And we compared our organic solar cells with silicon, with other types of solar cell. And we also considered different battery options. And then we did a calculation of how much energy would be generated, what would be the specific emissions, what would be the cost of the system, the cost of the electricity for all the different configurations. And we came out of that learning some things that surprised us. And the first thing, of course, with hindsight, they shouldn't surprise us, but they did. The first thing was that it's pointless to think about the cost of the electricity you generate, because even a standalone system, a lot of it is probably not useful or not going to be used. And we should actually think about the cost of the electricity that's actually used. The second thing, and this probably was the first thing that surprised us a bit at the time, was it actually was completely irrelevant, almost completely irrelevant, what sort of solar technology you used, so long as the lifetime was adequate. We did find that the cost of storage was very important, and that dominated the size of the system, and it dominated the cost of the optimum system. And we also found that the mini grid could actually be cheaper than the fossil fueled alternative if the subsidies on fossil fuels were not too high. So this actually was a critical thing. If the subsidies on diesel were absent in the case of India, then the solar mini grid would straight away become the cheaper option. Excuse me. So then that led us to think, okay, there's something quite interesting here to investigate, and we decided that we needed to make a more sophisticated model that could be used to design mini grids in a more flexible way and could actually be used in the field. So what we wanted for our model was something that could use kind of real data. And something, so nowadays there are, of course, data sources for things that are relevant, the solar and of course wind resource in different places. Demand data is a little bit harder to get, but we also work on that. And of course, there are up-to-date data on the costs of components and so on. So we wanted something that could connect to databases that are already available and out there to be connected to. We wanted a model that could be sort of continually developed, so that if some new technology comes along or some new idea comes along, we have the capability to sort of include it in our model system. And we wanted to be able to address a question which is actually very important in the context of rural energy access, which is how to integrate this solar mini grid with other power sources, such as a national grid, because most developing countries have an aspiration to extend a national grid across the country. That's very good in terms of energy access terms, but it can be slightly worrying from an emissions perspective, because the national grid nowadays will tend to be based on fossil fuels, and the emissions intensity of that power would be higher than the emissions intensity of a solar mini grid, but the cost would probably be cheaper because the grid may be subsidized as a large scale thing. It will tend to be cheaper. So that's an issue, this sort of trade-off between emissions and cost, particularly in the context of grid extension. So that's something we wanted to look at. And we needed to account for wanted to account for costs for greenhouse emissions and so on. And we wanted to have studies with which to validate the model. So it led to a model called CLOVER. So this is a kind of complicated diagram that shows everything that goes in. But basically we have technologies, we have data, and then it goes off and will solve. You tell it what you want to optimize. Typically, we tell it that we want to find the lowest cost solution, and then it will come back and tell us, how good it is, how much it costs, how much it emits, and blah blah, all of that. So, and it's an open source modeling tool. If anybody's actually interested, they're more than welcome to go to these links. If you miss them, then just put a question in the chat and I can put the links in the chat at the end, or the Q&A, sorry, I should say. So, so that's kind of summarizing. In many developing countries, so India is an example, but we've also got projects going on in sub-Saharan Africa, in Rwanda, in Uganda, as well. So we have a situation where the grid provision is kind of intermittent, if it's there at all. There's definitely an opportunity to provide energy access and reduce greenhouse gas emissions by using mini grids. And we've developed a model that we would like to use to investigate the possibilities. So just show some sort of examples of the sort of thing that we've been doing. These are results for a sort of a case which is based on a rural community in Uttar Pradesh. It's actually a community that we have been working with, and we collected usage data from this particular community. We have some information about how big it is. It's got some some industry there, which has this daytime demand. And these graphs are showing us during the hours of the day. So here is how much solar there is. Sun shines during the daytime. The demand, it peaks in the evening, just like it does here. But the demand for businesses tends to peak in the middle of the day. Of course, there's a nice match between the business demand and the solar generation. And then the other data we have here that's quite interesting is the data for the availability of the national grid at this location. And you can see it's quite spotty. Actually, there's a lot of the time, particularly during the middle of the day, when the national grid is not really available very much at all. The typical sort of on average, there's grid available for about 12 hours per day, which is not great. And obviously the demand, the overlap of the grid availability with the demand peak is not great either. The references at the bottom just tell us where we get our data from. And there are some nice online tools that provide information, let's say, about the solar generation and about the national grid availability. That's where our tool collects the data directly from those systems. So then we could look at some examples of results, and these are a bit sort of square diagrams, but I'll go through them. It's a way of kind of illustrating the methodology. So we've got a graph, all these contour plots. We take the first one, for example, and it's looking at really the question we're looking at is so if we go back to this for a moment. Supposing we have no solar mini grid at all, okay, and you're connected to a national grid, then you've got this availability. You've got electricity about 12 hours per day, but that doesn't meet what you need. So what happens? So what would typically happen is you have a generator running on diesel, and you would run the generator to provide electricity during the times when the grid is not available. So that's kind of the counterfactual. That's the situation that would happen if there was no solar mini grid. And then we introduce the possibility of having a solar mini grid that's got PV and batteries. And we give it to the model and we say, okay, go off and find the cheapest solution. And the condition we would give it is, say, find the cheapest solution whenever you want to provide electricity for, let's say, 22 or 20 or 12 hours per day. And you have at the same time as much PV and storage as you want, plus a grid that provides, and then this is the other coordinate, 12 or 14 or whatever hours per day. So you tell it what the grid provides, and you tell it then go off and find the cheapest way of actually meeting a demand of 20 or 22 hours of electricity per day or whatever. And then it fills in. And the numbers are telling us, and the color is telling us the cost of the cheapest system. And so if you have a grid that delivers an intermittent grid, and you want to have a high service, you have to pay. And the cheapest way of meeting that high service is with a system. So this is when we look at the next graph. This is telling us how much PV is in the system. So the cheapest system would be one that has a lot of PV. So in other words, it's easier to meet, that's cheaper to meet that gap in demand using a PV mini grid with current prices than it is with the diesel generator, which would be the alternative. And moreover, not surprisingly, that solution is also the greenest one. So it reduces the emissions intensity a great deal compared with the alternative of trying to meet, it sort of reduces the overall emissions intensities as averaged over everything from the grid and not the grid by a very great factor. So that's a kind of a sort of straightforward thing, sort of conclusion. It wasn't completely obvious it was going to be like that, but it is. But basically, if you have a grid which is only partly available, and you want to improve the access to electricity, the cheapest way to do that is to implement, considering the PV and diesel as options, PV is with batteries is the cheapest way to do it. And it also reduces the greenhouse gas emissions intensity. So if we want to increase electricity access, it's a win-win situation where the solar mini grid is both the cheapest and the greenest. And then we come to the sort of the thorny question, which is about, I'm sorry, this graph is not maybe very easy to read, but I'll explain what the main point is. The thorny question of what happens if the grid service improves. Does it then mean that your mini grid is no longer useful? And so we did some analysis of that, looking at improving the availability of the grid, and then finding the sort of the optimum system, the lowest cost system. And the thing that we made was a comparison between having the mini grid and the grid, and just having a grid. And having as you improve the availability of the grid, then the advantage in terms of your sort of electricity access decreases because the grid is becoming more available. And the greenhouse and the emissions intensity, so that's the blue curve, and the emissions intensity increases. But still, you're saving on emissions relative to the situation where you relied only on the grid, and you're also improving in terms of access to the service. So if the community is still willing to, it still wishes to have full access to the, sort of improved access to electricity, it's still going to be a worthwhile thing to do. So you don't, the mini grid does not become redundant. It just becomes less of a win-win option as the grid becomes better. And then we hope, of course, that over time, eventually, the grid itself will become lower in its emissions intensity as coal and gas are replaced with renewable sources. So that's the kind of where we are with that. Now, I'd like to go on now to comment, so you can say, okay, that's fine, that's all theory, so what? We have actually been using our model in a real life situation, and the background to it is that Phil, when he finished his PhD, he went off to spend a period of time working with an NGO called Practical Action, and the project that he was working on was to do with energy for displaced people. That was a project that the NGO was working with. And the situation is that with displaced peoples, it's very little attention until recently has been paid to things like energy access, because refugee camps are supposed to be temporary. And if they're temporary, then you shouldn't need to think about the sources of energy or whatever. However, of course, they're often not temporary. And there's globally, there is a humanitarian crisis with a very large number of people who displaced. So in 2019, there were about 70 million people displaced. And most of those people don't have access to electricity and are reliant on traditional fossil fuel heavy sources. So recently, through a number of UN international agencies and non-governmental agencies, there was a growth of interest in this question of providing electricity in humanitarian settings. And when Phil was working on this project, as soon after his PhD, he came back to visit one day and he said, the thing that these agencies need is a model just like ours, because they actually have no way of sort of figuring out how do we put things together in a sort of camp situation to sort of try to find the best, the solution with the best provision what will it cost, how should we design it, what emissions reductions will there be, and so on. So that then led us to a collaboration with, it was actually a collaboration with a company that does PV installations in Rwanda. They're called Mesh Power, and also with a refugee agency that works locally called Alight, and also with the UNHCR. And we then started work on a project where we were designing the PV system to go into a refugee camp called Mahama in Rwanda, where there's about, I think, 60,000 people living. And until the start of our project, there was only a diesel generator to provide the offices. And there was already a sort of a kind of a plan to replace the diesel generator for the agency offices with a PV system. And then we got involved and extended the project to provide also a PV generator, not only for the offices, but also for the health center and for the marketplace. And so that's a project. We got a little bit of funding for that from the fund called the Global Challenges Research Fund. Some of you may know about it. And the project kicked off in end of 2019, and unfortunately it was interrupted in early 2020 by the pandemic, but soon we hope we will be able to go back and complete the project. And the point, so we used our model to design the system, and I don't give the sort of details here, but the projections are saying that the introduction of the PV system is going to introduce substantial savings in terms of cost, because you don't need to buy diesel anymore, and obviously in terms of greenhouse gas emissions, because you don't need to burn diesel anymore. So that's quite an interesting application, and it's the first of its kind. And you know, depending upon how it works out, it may well be followed by others. So I've got kind of one more thing to talk about. I noticed that we're almost at 5:40, and I actually don't mind missing this and going straight to the end if there are questions. I mean, Athene, would you have a...
There are questions, but I mean, I don't know how long you need for this final topic.
5 minutes, maybe?
I'd be inclined to say wrap it up. I mean, sorry, wrap up the talk you have written. So have this last bit. Okay.
The last bit, it's just taking us, I can almost do this actually probably with two of the slides. All of this, a lot of what I've been talking about has been about energy systems for development, for sort of rural energy access. And you might say, okay, that's, you know, not the biggest problem that we face in terms of reducing carbon emissions. Although in the future it could be if we went the wrong way, of course. But we've also been sort of taking, I just want to comment on another thing we've been doing, and it's to do with energy accounting applied to mitigation options in general. And the context is this. I mean, you may recognize these. This is a figure which is taken from a special report on 1.5 degrees that was published by the IPCC in October 2018. And the different graphs are showing different pathways to meet net zero. And on the left, there is a pathway where you meet net zero by reducing your fossil fuel emissions very rapid. And on the right, there's a pathway where you reduce your fossil fuel emissions less rapidly, but at the same time, you try to remove carbon dioxide by using bioenergy with carbon capture and storage. So in other words, by using a carbon CO2 removal technology. And there's another which wasn't studied so much at the time, but it's been studied a bit more now, which is called direct air capture with carbon capture and storage. So BECCS and DACCS are these kind of two routes that are proposed to be ways of removing CO2 from the atmosphere. And this kind of question got us quite interested because the suggestion from these diagrams is that reducing your emissions and removing carbon from the atmosphere are somehow equivalent or interchangeable. but they might not be. And the thing that we did was to pay attention to, we were particularly interested in this proposal that's been put forward, that carbon could be removed and then used in something else. And the problem with sort of removing carbon dioxide and then using it in something else is that if you do anything to reduce carbon dioxide, you have to pay a lot of energy. And if you have to pay a lot of energy to do something which is removing carbon dioxide, then in the end, you might not have solved the problem. So we started to look at different options for carbon dioxide removal using a metric, which is how much energy do you have to pay to remove 1 gram, for example, of carbon dioxide. This is work that I did with Oyton Babakan. It was published last year. And so the point of this is that it's kind of like working out an emissions intensity, but not only considering electricity generation, but also considering things like removal of carbon dioxide using BECCS, or even this idea of converting carbon dioxide into something else. And then we were looking at, in each case, if in the end you have removed, X grams of CO2 permanently from the atmosphere, or hopefully permanently from the atmosphere, how much energy do you have to pay to do that? And I'm just going to zoom to the end, which is this graph. So we then defined our metric, which we call the carbon abatement energy. So that is how much energy, that's in its thermal equivalent, you need to pay per kilogram of CO2 that you removed, and then compare different things. So we compared, for example, this low carbon electricity. The example here would be if you were to replace a coal-powered fire station with a wind or solar generator. And then the cost in energy terms is quite low, because although you need to build a new power, although there's some energy embedded in building the new power station, you save a huge amount of CO2 by not burning coal. So that's kind of obvious. There's some things that are complete no-brainers, like replacing incandescent lamps with LEDs, or old-fashioned light bulbs with LEDs. Then you not only save energy, but you save carbon as well. And then the interesting things are then when we start looking at some of these other options. And so the options that were suggested as ways of removing carbon from the atmosphere, sort of like DACS, direct air capture, carbon capture and storage, and BECCS when used as electricity or as fuel, they are not nothing, and significantly higher in terms of their energy implications than it would be to substitute low carbon sources of electricity for high carbon sources. And indeed, they're more energy intensive than it would be to try to avoid emissions by generating and then using hydrogen. And then the idea of converting carbon into products where the CO2 is reduced are basically just ridiculous in energy terms. So that was kind of an extra direction that we went in, and that would be relevant to the sorts of decisions that have to be made in the future, where in a country like ours, where we're grid connected and we expect to be heavily dependent on renewables in the future, there will still be a gap of electricity supply that has to be made up by other sources. And I would argue it makes very good sense to think about those other sources, not only in terms of how much money they'll cost, but also in terms of how much energy they're going to cost. And those things are not yet properly taken into account in integrated assessment models. So to conclude, I'd say I expect solar photovoltaics is going to play a role in decarbonizing the future power sector in both developed and developing countries. And I've talked about a tool that we use to try to design the best solutions. And we were happy to find that the PV, the solutions based on solar mini grids, in many situations will be not only greener than the alternatives, but also cheaper. And we also have been able to use our tool in helping to design the system in humanitarian energy provision. And my final point is to say that more generally, I believe energy accounting can be critical in helping us to decide the optimum transition pathway. So that's it. And thank you for listening. And I'll just leave up my last slide where I thank some of the agencies that helped to fund us and my co-workers. Okay.
Thank you very much. That's absolutely fascinating. And there are a lot of questions already, but keep them coming. I will try and group them. So if I don't name the questioner, it's probably because I've amalgamated several questions. So the first question was about the materials that are used. It says, good news about the recyclability. How globally available are these materials, and will there be supply chain problems or trade diplomacy issues?
So if this refers to when at the start of the...
Yeah, I think it was a very early question, yes.
Yeah. So I mean, the materials that we work with, the sort of molecular electronic materials are basically based on carbon. So in terms of availability, there is not a problem. I mean, we have, I mean, probably Athene can answer that question as well as I can. But I mean, for example, we're not dependent on having precious metals or even toxic components. So carbon-based chemistry. There may be a question of where you get the starting material. Sometimes oil products can be used in generating starting products, but that's not the only way of getting them. A place where sort of materials availability comes up a lot is in application to energy storage. And we're kind of using organic materials as sort of energy storage is at a very, very early stage, but they are quite interesting in the sense that the materials seem to be compatible with sodium rather than lithium-ion batteries. And you don't, I mean, you don't use heavy metals, so you don't have a problem of availability of cobalt or nickel, but on the other hand, you lose in terms of the volumetric capacity. So there's a performance penalty. And then in terms of how recyclable they are, I mean, of course, there isn't yet a recycling industry, so it's quite hard to point to that. But the sort of the recycling aspect is something that's being taken into account in terms of research. So people are definitely looking at using non-toxic components and at making structures where layers can be removed from one another by some kind of processing. Of course, not too easily removed because you don't want them to fall apart when you're using them. But that is, I mean, there's actively research going on in a kind of circular economy aspect in terms of thinking before you even get into a manufacture, what are what components would be compatible with the recycling sort of mode of use.
There are various questions about the model, and I will endeavour to wrap them up all in one question.
Yeah.
So things like, what is the largest source of error in the modelling? How much can you introduce other possible sources of energy into your modelling, be it wind or something like that? And what about the different, I was going to say length scales, it's not length scales, but different scales of abstraction feed into the model?
So could you repeat the last one, Athenia?
It was the different, I find it hard to think of the right word as a microscopist. I think of length scales, but the different scales, the different levels at which you are doing the model, how much you're aggregating together.
Yeah, sort of the multi-scale aspect of it.
Yes, thank you, yes.
Okay, so I'll take the second one first because that's very easy. So I mean, wind is already there. We have a wind module, we have a diesel module, we have a hydro module. Something that we don't have at the moment, and we're actually working to do this with a PhD student who started recently, is include a solar thermal module, because it would make a lot of sense to kind of integrate solar. It makes a lot of sense to integrate solar electricity and heat anyway. But that's something that we're working on, and so the module, the model is written in Python. It's kind of there, open source. If somebody wanted to use it and add in a new module to do something new, they could. And we've also used it actually for different situations. I was talking about using it for village electricity in this talk, but we've also used it to look at things like generating self-charging electric vehicles. I mean, you can't of course completely charge an electric vehicle by having it sit in the sun, or at least you couldn't drive it very much if you did, but it can contribute something like 10% of the electricity needs. And we've actually used this model to model that sort of balance of demand and supply with electric vehicles. So other energy sources, yes, that's easily done. Biggest sources of error, I mean, I guess one thing that is quite difficult is to have a good projection of how demand is going to develop over time. You know, I mean, there will be, I'd say probably the first thing to say is that the biggest sources of error are probably not technical or technological. They're probably more to do with the sort of social, you know, economic and political factors. So we don't really know how costs are going to develop in time, and we don't know what's going to happen with subsidies, for example. We don't know how demand will develop exactly. I mean, we do work where we talk to people, we talk about aspirations, we see what has happened over the course of maybe 2 or 3 years in a system we've been monitoring, but in 20 years, we don't know how that's going to change. We don't know how, you know, demographics, how I mean, so to say the biggest sources of error are probably kind of, you know, social, economic and political. If the question is how well does the model predict the actual performance and cost. There would also be sort of technical sources of error in terms of things like how components are used. So for example, the lifetime of batteries depends quite a lot on how heavily they're discharged. And if they're discharged too heavily, they don't live for a long time. And so that's something which you might model it as though the batteries are treated perfectly, and then in practice they might not be. So that would be a source of error. And then in this bit about how different scales of the model feed into each other. I mean, so that's quite a good question, because when we started off, we sort of did things more or less in the chronology in which I presented them. And we started off doing quite a detailed life cycle analysis of solar cells. And then we wanted to compare our organic solar cells with other solar cells in a model. And then what we did was of course, we hadn't then done a life cycle analysis of silicon and cadmium telluride and so on, but we looked at what had been done. And so we grouped together things that were, so we grouped together all of the costs and energy. So we separate out electrical and thermal energy requirements. And we would then group together the sort of, if you like, the amount of energy that's embedded in the materials, electrical and thermal. And we would separate out costs that were compared relevant for per unit capacity with those that were concerned with the balance. So we'd separate out capacity related and area related costs. And then we would have also the balance of systems, and that would be something that we would also use those sort of costs, those energy costs, in quite an aggregate way, but we would apply the same balance of systems. So that means kind of like the inverter, the wiring, the mounting systems and things like that. And we sort of try to use the same, make the same assumptions for different PV technologies as a kind of default. That's not necessarily the right thing to do, because in practice they might be used differently, but it does make for kind of fairer comparison. So we did have to aggregate the different components when we went from doing one technology to doing a comparison of different technologies. And the model as it stands contains kind of aggregated energy costs for the materials that are needed for the module, and then something different for the balance of systems, and something different for the battery, and so on. I don't know if that helps to answer the question, but
well, let me give you another one. So again, I'm amalgamating questions.
fine.
So the question is, you've talked about what happens in the developing world, and the question is, partly, does PV have a future here in the UK? I mean, there's an awful lot of stuff going on, but not with organics, of course.
Sure.
And then
sure.
how long does a typical PV panel have to produce electricity for before it breaks even in terms of energy? And again, I'm assuming that actually refers to the standard silicon panel rather than.
So the break even in terms of energy is kind of typically for silicon, I believe it's around between 1 and 2 years. And that would be for a module that would be designed to last for 20 years. And they may actually well perform longer than that. I mean, so it then takes us a little bit back to the recycling question, because when a PV panel breaks, it's not the semiconductor that breaks, it's probably the contacts, the diodes, or maybe even the plastic stuff on the top gets degraded and starts scattering the light rather than letting it through. So if you ask for the sort of another metric, which is the energy return on energy investment, it's about a factor of 10 for PV, and for the modules it can be much higher than that. But when you think about the whole PV system, it's probably more like 10 or a bit less. So 1 or 2 years. Now I'm forgetting the rest of the question.
Well, the question was, does it have a future in this country? But I suspect that was actually directed towards the kinds of things you're talking about rather than the solar farms.
Yeah. So does it have a future in this country generally? If we look at the projections in the recent 6 carbon budget that's produced by the Committee for Climate Change, for example, we expect that the majority of electricity is going to grow, because electricity needs to meet transport and heat to a large degree, as well as things that are traditionally electric. And most of that is going to be something like 75%, I think, of that is going to be wind and solar by 2050, or at least that's one projection. Most of that will be wind. But probably something like a third of the renewable generation, I imagine, will be solar. Now, is it going to be from OPV? Probably not. The place where, and I mean, that's because, over the time I've been working in this area, the cost and the energy required for making silicon solar cells has just come down absolutely massively through economies of scale. And the cost of the PV panel is no longer a showstopper. It's other things that need to be dealt with. So I think that the dominant solar technologies is already quite good. It could get better. And there are ways in which PV technology could get better by combining silicon with other materials, for example, in tandem structures. And if you can find something which is kind of easy to process and has the right band gap, and you could put that directly on top of silicon, you could make a tandem, you could increase efficiency, and that could be made from some of the newer materials that people are working on today, perovskites, for example, which are studied a lot in Cambridge, amongst other places. And organics could potentially become part of that as well. So maybe in future PV technology, there may be a role for our materials, sort of at this kind of solar farm level. But then there's another side of this, which is using PV for kind of sort of mobile power, communications, and so on. So for remote sort of unwired power sources. And I think there's a huge potential there. And that's a place where the sorts of materials that we work on could be used. So when you want to kind of connect through communications or whatever, you want to have remote power sources and sort of materials which have a lot of flexibility over how they're made and how they're integrated with batteries, whatever, would have a future there. So that's sort of answering two different questions.
No, that's absolutely brilliant. I'm conscious that we're losing our audience because we've come to the end of the hour. I am also conscious there are a lot of questions we haven't answered, and apologies to all of you who put in questions, but this is such a rich and important topic. I'm not surprised there are many, many questions. So it just remains to me to thank Jenny very much. I look forward to seeing her come back here sometime in reality, not just sitting in Imperial and giving us a lovely talk. So thank you so much. That's been very illuminating, and I hope the audience has enjoyed themselves. We can't get a round of applause, but imagine it.
Athene, I'm perfectly happy to try to answer questions that are in the Q&A. I mean, if the platform remains open, I'd be quite happy to write something against things I could answer. Is it sensible to do that, or will everybody have gone?
I suspect people will have gone, and we don't have their email addresses.
I see.
Sometimes you can sort of contact them afterwards, but unless.
Okay. Well, I mean, let me leave it like this. So, I mean, I'm perfectly happy for somebody to contact me. I mean, I'm quite easy to find, but basically it's jenny.nelson@Imperial. And yeah, feel free to get in touch if there's something, if anybody has a question they particularly want to follow up that we didn't have time to deal with.
Well, thank you very much. That's very generous of you. And I hope the audience have taken that on board. So thank you so much. Thank you.
Okay.